Hmm. So we saw the method of OLS. Now the method of OLS for the linear relationships. That how do we find the slope for the using the covariance formula of x and y and divided by the variance of x, we get the slope of the x variable, right? So, but what if this only works for the linear relationships? But what if we have a non-linear mapping such as e to the power x as a feature, x square as a feature, x to the power 2 power 3 and x to the power 4 of 5. So which are common in any domain. So the features are not linearly dependent, but non-linear dependency of features is there. So how do we get to know what is my slope, as the feature is something like this, the slope is constantly changing, right? There is no one slope value that can determine what is my slope value. So we look at the instantaneous rate of change, which is how my x changes with y at this particular instant. So it is a concept of derivative. If I take a very small step in 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 this direction, so would my y increase or decrease? So let's say we are here and we take a very small step in this value. Would my is my y is my delta y by delta x increasing or decreasing at that particular instance? For this instance it might be decreasing, decreasing, and it is constantly decreasing. So this would be a negative slope, right? So my change in x is having a negative slope on y. So we need a derivative. We need to just simply compute the derivative to find the instantaneous rate of change. So let's say for multiple variables we need to compute the partial derivative, and the vector of the partial derivative becomes my gradient. Derivative of loss with respect to x1 sorry, it's not x1, it's w1 respect to w2 and respect to w3, and the list goes on. So this is my becomes my gradient vector. So, and I'll make small changes in the direction of the gradient and check whether my overall loss is decreasing or not, right? So let's say, how should I check? Let's say for using the gradient descent formula, which says j theta is theta minus theta into d theta. So theta is my weight and this is my derivative of it, and n is the learning rate. So, or we can say the step size. So how much should I update based on the learning rate. So why we have a minus sign here? Why not a plus sign? If I find a slope, let's say here, so why I want to go in the opposite direction of the slope? Why not go in this direction? Because as we go in the direction of the gradient is always pointing towards the maximum extent. Let's say if we go in the direction of the gradient, we'll reach the maximum of the function. But this is an optimization problem, so we want to reach the minimum of the function. So it is also why gradient points towards the maximum of a function is given by directional derivative. Let's say if f is a multivariable function where the moving in which direction would cause my function to increase the most. So the direction is given by the unit vector u, and p is the point where the derivative is evaluated. and h is a tiny step approaching 0. So if we take a small step in the direction of u, how much my overall function value changes. So it can be, so to find the alignment between the direction unit vector and the gradient vector, we compute a dot product. So just to check whether how much they align. So this can also be written as norm of the function into norm of unit vector to cos theta, as we are computing the dot product. And this norm of u is 1, and so norm of function b will give you the magnitude of the vector. So to get a maximum step, in which direction should I move so that my magnitude is the highest and I'll reach the maximum the fastest? So it depends upon the cos theta. So cos theta lies in the range of -1 to 1, and if I want the magnitude to be the highest, I'll choose theta is equals to 0 and cos theta equals to 1. Therefore I should move in the direction of the gradient to get the maximum magnitude, right? But it is also only the magnitude, right? But if the same magnitude is leading me towards a maximum of function, if I go in the opposite direction of the function, say theta is -1, I'll reach the minimum of the function, right? So in gradient descent formula we have the minus sign, which is j theta is theta minus eta into derivative of the function with respect to the weight. So this is the gradient descent, which is used across many algorithms. So there are many types of gradient descent used in industry. One is SGD, second is batch, and third is mini batch. So let us discuss one of them one by one. SGD can be slower to converge as each data point is causing the weight to change. So number of updates is higher, as number of updates is equals to number of samples, because each sample is causing my weights to change. But in a batch gradient descent, we are processing the entire data set at once, computing the gradient across all the data points and averaging out the gradient values and providing a single update. The number of update is, we only update the weights just once, so it is not too rigid. So my model gets only one weight update, and it can be, if the data set is large, my memory can bloat, or it can explode also, or my computer can hang, whatever we call it, right? Gradients are generated average across entire data set, chances of getting stuck at local minima and never reaching the trend. So let's say for a non-linear function like this, so what if we reach here and my local minima, this is my global and this is my local, right? So I want, this is less than this, so I want to reach here, but if I use just one gradient update, I might end up here, the local point, not the global point. So instead of using the batch gradient descent, I use mini batch gradient descent, where I divide my entire data set into n batches, and n batches are, and each batch updates my weight, so the next batch will get the updated weights, and this goes on for the across the n batches. So my number of updates will be n, which is my batch size. So this is widely used in industry because it has, you know, more accurate, more accuracy, chances of getting to the global minima is higher, chances of getting to the global minima. And yeah, and it is dealing with the high high data, high, what you can say, high data, huge amount of data. It can deal well with huge amount of data, though it introduces a hyper parameter, the batch size, which the data scientist needs to fine tune, but it can handle, it can output with more accuracy and handle huge amount of data. So this is the gradient descent in summary.